Welcome back to ViViMaT. Our next speaker, Cangyu Qu, is a research fellow at the Institute of Superlubricity Technology at Tsinghua University in Shenzhen. He was recommended to me by Rob Karpik from University of Pennsylvania, which says a lot. I made the mistake of going to his Google Scholar profile and got a whiff of his publication record. This guy has contributed to so many articles in journals like Science Advances, Physical Review Letters. It's crazy. Certainly puts me to shame. I'm looking forward to his talk on superlubricity right after this message from our sponsor.
Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, superlubricity.
Hello everybody, welcome to my talk, and thank you Stephen for inviting me to this wonderful workshop. I'm very grateful to share some of my recent works that were performed when I was a PhD student at Tsinghua University, China. So the topic is friction origin and characterization of a superlubric graphite contact. As tribologists, we all know that the friction and wear are very important phenomena. They're scientifically fundamental, happen everywhere, and also very important for industry and economy. And there is a fascinating phenomenon called structural superlubricity, which is possibly a solution to the friction and wear problem. It refers to the phenomenon of nearly zero friction and wear between directly contacted solids. And it's actually a multidisciplinary field that is attracting more and more interest, and many breakthroughs have been made in the past decades. So there is a perspective paper on it, which I recommend if you want to learn more about it. Well, actually, there are different definitions of the word superlubricity. But here in this talk, I will only focus on the one simplest form of superlubricity, which is the superlubricity of an incommensurate crystalline contact. So imagine that you have two perfect crystals brought into contact. If they share a common periodicity, we call this contact commensurate. However, if one of the crystal is rotated with respect to the other so that they do not share a common periodicity along the sliding direction, as you can see here, we call this contact incommensurate. The sliding behaviors of commensurate and incommensurate contacts are completely different. To see this, we first model the contact by a so-called one-dimensional FK model, where one side of the contact is modeled as a rigid potential surface, where the other side is modeled as an infinite chain of atoms connected together by springs. So if the contact is commensurate, the lateral forces acting on each atoms of the chain add up coherently, and that leads to a large overall friction. But if the contact is incommensurate, because the chain and the potential surface do not share a common periodicity, when you add up the lateral forces on each atom, you will find that they cancel out systematically. So the overall friction is zero, and the chain can slide on top of the potential surface freely. And that is when superlubricity happens. That's not the whole story. Even if you have an incommensurate contact, to maintain superlubricity, the interlayer interaction has to be weak enough. That is because if the interlayer interaction is too strong, the potential will force some of the atoms to be pinned on the bottom of the energy wells. And once this so-called orbital transition happens, you will need to overcome a large friction force to slide the chain. So to make sure the interlayer interaction is indeed weak enough, layered material is a good choice for superlubricity. Usually they have chemical bonds within the layer, which ensures a relatively high in-plane stiffness. That is a high stiffness constant for those springs. Meanwhile, the interactions between the layers is the weak van der Waals interactions, and that ensures a weak interlayer interaction. The basic concepts of superlubricity are built on perfect crystals. But for practical superlubric contacts, things are a little bit complicated. One important difference is that practical contacts must be finite sized, so they will have edges. The edge atoms will have lower stiffness than inner atoms because they are less constrained. And when the contact is exposed to ambient air, there will be adsorption and contamination that may lead to edge groups or dangling bonds. And this raised the question, in a practical superlubric contact, is the friction mainly from the contact area or from the contact edges? Theoretically, there are indeed some works looking into the edge effect of superlubricity, but experimentally, it is very challenging to decouple the contribution to the total friction from edge and area. And that is the starting point of my work. So my work is mainly performed on a previously developed system called the graphite mesa. They are micrometer-sized pillar-like mesas fabricated from highly orientinated pyrolytic graphite, HOPG. Well, HOPG is a kind of graphite that is multi-crystalline. Among one single grain, the graphene layers just stack on top of each other. But at the grain boundary, the lattice orientation of the two adjacent grains are naturally twisted against each other, as shown here. So that means these twist grain boundaries are naturally incommensurate interfaces. And one graphite mesa contains many numbers of those grain boundaries, the twist grain boundaries. So when the mesa is sheared by a tip, it starts to slide at one of these twist boundaries. And what's fascinating is that when you release the tip, some of the mesas immediately retract back to the original position, as shown in this video. And that is because when you slide away the top flake of the mesa, you actually increase the total surface energy because you are exposing new surfaces. So there will be a retraction force that drives the sheared mesa back. And here, the large gamma is the so-called cleavage energy, which equals 2 times the surface energy of graphite minus the grain boundary energy. And B here is just the width of the mesa. Well, as I mentioned, only part of the mesas can indeed have very low friction and show this self-retraction motion, while others have relatively large friction and just stay at the sheared position when the tip is released. It's a very interesting question why only part of the mesas are superlubric and show self-retraction. And I will talk about it later. But right now, let's first focus on the mesas that are superlubric and show self-retraction. For these mesas, we can measure the friction force using atomic force microscope, AFM, which is a very common equipment in nanotribology. We use the tip of the AFM to press on top of the mesa and slide the top flake back and forth and record the lateral force signal at the same time. So the friction will be the area enclosed by this so-called friction loop, which corresponds to the dissipated energy, divided by the travel distance. The measured friction force for a 4 micron mesa is typically on the order of a few hundreds of nanonewton, which is indeed a very small friction. And we can move the flake, the top flake, to different positions and repeat the measurement of friction. At different positions, we have different contact area and different lengths of total contact edges. And if we simply assume that the total friction is the sum of contributions from contact area and contact edge, we will see that the friction should be a linear function of x, which is the displacement here. And here we will see that there are 3 parameters, which are friction per edge atom per edge atom or friction per edge atom. And the idea is by doing measurement and fitting for mesas with different size and shape, which means different B and L, which are lengths and widths of the mesas. We should be able to extract these 3 parameters and decouple the contribution to the total friction from contact area and contact edges. Though that we have actually 2 kinds of contact edges. F parallel here is the edge-to-edge contact, where F perpendicular here is the edge-to-area contact. But later we will show that they are almost the same. We will see that the intercept of this linear function actually contains the parameter F perpendicular, while the slope of this linear function contains FA and F parallel. By doing the fitting and measurements on mesas with different weights B, we find that on average, each edge atom contributes a friction of roughly 1 piconewton. And meanwhile, the friction from an area atom is nearly zero. I must explain that we do not know the exact number for Fa, since you can see that the standard deviation and the mean value is actually on the same order. But what we do know is that the friction from an area atom is at least 4 orders of magnitude smaller than that from an edge atom, based on the estimation here. Note the difference in the unit here. Now we have these numbers. A further question would be, what do the contact edges and contact area look like? Why does an edge atom contribute a large friction while an area atom does not? For the edges, the scanning electron microscope images show that they're in fact not straight, but with those kind of nanoscale corrugations. So the actual length might be different from the apparent lengths of contact edges. An X-ray photoelectron spectroscopy results reveal that the edges are actually not entirely composed of sp2 carbon, but instead they have chemical groups. And those chemical groups might be from the fabrication process, because we used a reactive ion etchant to fabricate the mesa by oxygen. So during the sliding process, these edge groups might act as pinning sites and lead to a large edge friction. Meanwhile, to see the contact area or the contact interface, we need to first expose both sides of the contact interface in the mesa. And we do it by a so-called flipping technique, where a tip is used to slide the top flake and flip it upside down, so to expose both the upper and the bottom sides of the contact interface. And then both the upper and lower surfaces are scanned using an FM working in the lateral force mode, where height and friction of the interface of the surface can be measured simultaneously. For those mesas that show superlubricity and self-retraction motion, there are 2 cases. The first case, the interface is just atomically smooth and flat with sub-nanometer roughness. The height images and the friction images are just uniform and show no significant structures. Meanwhile, in the second case, the height images show some steps appearing as abrupt changes of height, but these steps do not have corresponding signals on the friction map, and they are known as internal steps, like the sketch shown here, where B is an internal step. So they are steps buried underneath the topmost layer, so that they lead to a height signal but no friction signal. Of course, since there are internal steps, there will be external steps as well, just like the 2 steps labeled by A and C here. They have signals both in the height image and in the friction image. I will talk about the external steps just in the next slide. Now, for these 2 cases, the contact will be superlubric. And the interesting thing is that as long as the contact is superlubric, the friction contribution from the contact area is almost zero, no matter the interface is atomically smooth or with internal steps. And the dominant part of the total friction is from the edges. And this can be seen here in this plot, where friction is measured for 3 different examples. Examples 1 and 2 are examples with internal steps, while example number 3 is example with atomically smooth interface. But you can see that their friction are all very small, which suggests that they are all superlubric. And if you define the slope of the friction force versus normal force curve as the friction coefficient, you will see that the friction coefficient is also very low for all the 3 examples, which is also a feature of superlubricity. As I mentioned a couple of slides ago, there is an interesting question why only part of the mesas are superlubric and show self-retraction while others do not. Now we can answer this question. We expose and characterize the interfaces of these mesas without superlubricity. We found that these interfaces have external steps shown here. And those external steps usually lead to high friction, as the case of this example 8 here. So the friction force is nearly 10 times larger than the superlubric masses, and the friction coefficient is also significantly higher. And this mechanism can be confirmed by molecular dynamic simulation, where we found that atomically flat interface and interface with internal steps have almost the same very low friction. But an external step increases the friction by nearly 100 times. Since the external steps are so important, they lead to high friction and in many cases, the failure of superlubricity. A further question would be, where do they come from? There are two possible scenarios. The first possibility is that there are actually fractures of graphene layers during when we first share the mesa for the very first time. If that is the case, where there is an external step on one side of the interface, there should be exactly another step on the other side of the interface at the coincident position. And the second possibility is that those external steps are pre-existing defects in the material. If that is the case, there does not have to be such coincidence. And our results show that most of the external steps do not show this kind of coincidence. That means they are pre-existing defects in the material. And that is actually a key challenge on large-scale superlubricity, because these pre-existing defects randomly distribute in the material. And if you fabricate a mesa, there will be a chance that this mesa happens to contain such a defect. And that very likely leads to high friction and failure of superlubricity. When the size of your mesa increases, the chance of having such a defect in your mesa also increases. So the probability of having a superlubric mesa drops. Right now, the size limit of superlubric mesa is on the order of tens of micrometers. And to achieve larger scale superlubricity, we need to have materials with very few defects at the interface. Okay, so to sum up, we use the graphite mesa system to show that friction in practical superlubric contacts is mostly originating from the edge. And that is likely because there are geometric corrugations and chemical groups at the edges. The edge originating friction also provides us with some guidance on the shape design of superlubric devices. For example, if you want to achieve the lowest friction possible, you should try to reduce the total length of contact edges. To understand why the contact area does not contribute much to the total friction, we characterized both sides of the contact interface. And we found that superlubric interfaces are either atomically smooth or with internal structures, but the friction force are both very low for the two cases. Meanwhile, some dampers have external steps, and that usually leads to a high friction. And the findings tell us that to achieve large-scale superlubricity, a key challenge is to find superlubric material with very few defects at its interface. Okay, thank you for listening, and I hope you find our research interesting. I would like to thank my PhD supervisor, Professor Chuanshui Zheng at Tsinghua University. All of my work is performed on the graphite mesa system developed by him and his previous students. And here are my colleagues at Tsinghua University and the Institute of Superlubricity Technology. And I also want to give special thanks to Kunqi Wang and Jing Wang, who are my colleagues, and Professor Robert Kopik from University of Pennsylvania and Professor Michael Erbach from Tel Aviv University. The works presented here are mostly included in these two publications, where you can find more details if you are interested. And of course, you are more than welcome to contact me if you have any questions or comments. Thank you.